pleasure to be introducing Hal Walker, who's giving the seminar today, and I guess first seminar of the semester. And for those faculty who are here, I've nominated Hal to be a joint faculty member here at SoMAS, and so you are to send your comments and feedback to Dr. Larry Swanson after this, so that we may move forward. Hal is with my faculty. Brief background on Hal. He's an engineer. He's from the civil engineering department. So he did his engineering degrees on the West Coast. He's a West Coast native. Went to Cal Poly for his undergrad and got both his master's and PhD degrees at UC Irvine. Thereafter, he became a professor at Ohio State University, moved up the ranks to professor, and became their director of water resources. Of course, there's one for state. He was the director for Ohio there. And well, you can say a lot of things about Stony Brook University, the good, the bad, and the otherwise, but I think one of many great things going on was the strategic hire of Hal and bringing him to Stony Brook. Well, you know, before Hal came here, we didn't have a civil engineering program, which is kind of remarkable. So he started the civil engineering program here. They're actually graduating their first class this spring. They have more than 120 students, and in addition, I just told me that he and Henry just got approval for their advanced graduate certificate in coastal zone management engineering. So graduate students can get a certificate in this by taking 4 classes, 2 here at SoMAS, 2 in the engineering program. And I first got to know Hal because I knew about his research on cyanobacteria and cyanobacterial toxins. But thereafter, actually, we've become co-directors for the Center for Clean Water Technology, New York State Center for Clean Water Technology. And it's been a real pleasure working with Hal. He's got a lot of energy and always a positive attitude. It's helping us steer things in the right direction. And so, with all that being said, it's my pleasure to introduce Dr. Hal Walker.
Well, thank you, Chris, and thank everyone for coming. I need to turn this on. You okay? Yeah.
That was more introduction more than I deserved, but thanks, Chris. I really appreciate it. Also, I don't want to take credit for the advanced graduate certificate. I played a pretty minor role, because many other people in this room were contributors, but it is available, and so we encourage you to start that. Also, we have 121 students in civil engineering. Only 13 are graduating this year, so that's 121 total. Just some clarification. I'm very happy to be here today to talk about some work on the drinking water side because, as Chris mentioned, we've been working with the Center for Clean Water Technology on the wastewater side, so it's a little cleaner on the drinking water side, so it's fun to talk about that as well. And hopefully the topic will be of interest to you. It's going to be a little bit of engineering, but then also a little bit on harmful algal blooms or cyanobacteria. And so I'm going to talk really about the issue of cyanobacterial cells and toxins in drinking water and the current status of technology in this area in terms of drinking water and some of the research that I've been doing with my research group over the last few years looking at novel ways to remove these and keep the drinking water safe. If you have any questions, please feel free to ask them as we go along. Okay, so what I want to talk about is first, I know this is a marine systems school. I'm sure you have interest in freshwater, but I thought I'd give a little bit of background on the occurrence of freshwater cyanobacterial blooms. There's lots of different names. One are cyanohabs. I know they're not algae, I guess. I'm not an ecologist, so bear with me. I'll talk a little bit about the different types of toxins and the type of toxicity that they generate as background. I'll go over a little bit about how we treat our drinking water and the implications of current technology on removing these particular cells and toxins. And then I'll end with looking at some of the more novel advanced processes that we've been doing research on. Okay, so one of the first instances of a cyanohab in a freshwater system dates back to about 1876 in Lake Alexandrina in Australia. It's on the south coast of Australia. And this is a paper that was published in Nature in 1878. And it documented the occurrence of a toxin called nodularin. It's one of the cyanohabs. And what they found was that a number of livestock, cows, sheep, drank water from the lake and with nodularin and immediately died. So this is really considered one of the first published cases of poisoning. It wasn't human poisoning, it was animal poisoning as a result of a cyanohab. And nodularin is one of the classes of cyanohabs. It's one of the larger ones, and it's a peptide ring. There's 5 different peptides, and then it's called ADDA moiety on the end. And this is a typical structure. There's different variants. As you can imagine, with peptides, you can have different peptides substituted in here. And so I think there's over 50 or 60 variants of this with different toxicities. Kind of move forward into the future here. Toledo, Ohio, probably many of you may have heard about this. In 2003, there was a large bloom of cyanobacteria in the western basin of Lake Erie. So this is Lake Erie, the western half of it. Cleveland's right here. Guess we're down over here. And Toledo is right about there, so you can see in this map. And the intake, where they get their drinking water, is a pipe and an intake crib that goes into Lake Erie. And on this map here, it's right about there. So you can see it's right in the middle of the green muck of microcystis. There's also other towns. There's a small town called Oregon on the bay of Lake Erie. Their intake structure is right next to it. Monroe, Michigan is right up here. So millions of people rely on Lake Erie for their primary, only source of drinking water. This particular bloom shut down the water supply for the city of Toledo for 3 days. So no water coming out of the tap for 3 days. And the toxin was microcystin, and it's similar to nodularin in the sense that it's a cyclic peptide. In this case, there's 7 peptide rings in this ADAA group at the end. And again, because you can substitute different peptides in here, there's, I think, over 70 or 80 variants of this with different toxicities, different physical and chemical properties. So nodularin and microcystin make it challenging from a treatment point of view because there's all kinds of different properties, and so it can be challenging to design treatment processes to remove them. Now coming over to New York, there's a monitoring system in New York, and they issue blue-green algae bloom notices. This doesn't necessarily mean that they're toxic, but they're suspected to be toxic blooms of cyanobacteria. And this is Roth Pond. I don't know if did anyone see the notices last year? I guess you don't see too much over here. Ollie, you saw it. But this is right next to my office. I was going out for lunch, unsuspecting, walking around, going for a walk at lunch, and oh my gosh, it's a harmful algal bloom right in my backyard here from my office. I can actually probably see it from my office window. The state DEC collects data every year on these notices, and the first data I just looked online, the first data they had available was in 2012. There are 51 notices, and the number of notices has increased every year. And this mirrors sort of what we see at the national level. Whether or not this means there's more blooms or more awareness is a debatable point. But at the very least, there's more recognition that these blooms are occurring and having an impact. This is sort of the national level. Some of you may have seen this if you work with harmful algal blooms in marine systems, because obviously we have the coastal systems here. But the little green circles here are the cyanohabs. And so what you can see is these are documented, confirmed cases of detection of cyanohabs and cyanotoxins in different states. And as of now, at least 35 states have documented occurrence of cyanobacteria. So it's very prevalent across the United States. I mentioned Australia, so it's a global issue. Here are some of the toxins that we talk about in these freshwater systems. I mentioned microcystin LR, but as I mentioned, there's many variants of this. Nodularin I showed you. And then there's smaller ones. There's cylindrospermopsin, anatoxin, and saxitoxin. You may be familiar with saxitoxin. I think this is what is it, paralytic shellfish poisoning, but it also occurs in freshwater systems. But these are really the main classes of cyanotoxins that we think about with respect to these freshwater blooms. And as I said, the molecular weight, even within a particular class, varies a lot. But then you've got anatoxin is the smallest molecular weight, about 165, and microcystin is the largest. They have different acid-base properties, so their charge can vary over pH in different conditions. Some are hydrophilic, some are more hydrophobic. So these properties are important in terms of the treatability of them in drinking water. So when we talk about cyanohabs and cyanotoxins, we're really talking about a diverse set of chemicals that we have to try to remove from our drinking water, which is a challenge. Their toxicity is still, the toxicologists are still learning about this, but they're confirmed liver toxins, and they also affect the kidney. So nodularin, microcystin, cylindrospermopsin, and anatoxin and saxitoxin are neurotoxins. There's many other health effects that have been identified, chronic as well as chronic and long-term effects. In terms of some of the effect levels, if we go the highest level, the LD50s, lethal levels in mice at least are on the order of 5 to 10 milligrams per kilogram. And if you want to see no effect, the NOAEL, I don't know if you have any experience in industrial safety and health, but this is the no observed adverse effect level. Okay, so below that, nothing's supposed to happen. So you can see that's a lot lower than death, of course. Hopefully. So those are pretty low, and then and these are acute, and then you can think of subchronic. These are reference doses, so these are more chronic or subchronic effects, and these are even lower exposures. So the point is some of these are not known, and if we start looking at no effects or some of these subchronic effects, we're really getting to very low concentrations. And that takes us to regulatory needs. So the next question is, well, how much is safe, and how do we maintain safe levels in our drinking water? Currently, there are no federal limits on these compounds in our drinking water. So it's not something that the local drinking water treatment plant has to test for, or if they're over at a certain level that they get a citation for. So at the federal level, we have these things called maximum contaminant levels, MCLs. So there's none at the federal level. However, EPA does publish what's called the CCL. It's the Candidate Contaminant List. There's roughly 100 different compounds on this list, all different types of compounds. And it's a list of chemicals that's the EPA is investigating to potentially develop a regulation for. And the 4 means it's the 4th list they've come up with. So there's a CCL 1, 2, and 3 before this. This just came out. It's open for comment right now. And currently, anatoxin A, microcystin LR, and cylindrospermopsin are on that list. So they're being reviewed for the development of potential regulations. They were on CCL 3 as well, but no action was taken, and they were sort of punted onto CCL 4 for continued evaluation. States are able to implement their own drinking water regulations. There are no state standards in the United States. There's not a state in the U.S. that has adopted specific standards in drinking water for these compounds. A number of states, though, have guideline values, so they're not enforceable. One of the few actual limits that's been put out there was developed by the World Health Organization, and they've suggested a provisional limit, or it's a suggested limit of about 1 microgram per liter for microcystin LR. Some other countries have developed standards anywhere from roughly half a microgram per liter to maybe 1.5 for this compound. So there's some consensus that around 1 microgram per liter is sort of the safe level in drinking water. But this is still under development. Okay, so that's sort of the background in terms of these compounds, the different types of compounds, their significance, toxicity, and kind of how we treat them in the drinking water system. I want to move now into the treatment aspects. And so in water supply, what we typically try to think about is what's called a multi-barrier approach. You don't want a single technology or a single option to deal with the problem completely. So you want multiple levels of defense against things like these toxins. So if we think about the cyanotoxins, the different levels that we can think about are source control. So if the toxins don't exist in the lake to begin with, or the water supply, that's the best option. I'm not going to talk about that option. Sure, many people in this room know more about this than me. So I'm going to talk about once it gets into the water treatment plant. Water treatment plants across the country look remarkably similar. They use very similar technologies. And so I'm going to call this conventional treatment. Many of them, or most of them, also utilize some kind of oxidative treatment. And then some of them may have more advanced treatment. So I'm going to talk about, in particular, these 3 categories of technology that you might see in a water treatment plant, and how effective they are for removing these toxins. Conventional treatment, the primary goal here is we want to remove the cells. So these are these cyanobacteria. We want to remove the cells without breaking them apart and releasing the toxin that's inside them. So that's really the goal here for conventional treatment. Once we get to oxidative treatment, if there's any toxin in the water, we want to try to destroy that toxin as much as we can. And then if these 2 approaches don't get us to where we want to be, we need to provide some kind of advanced treatment. And 2 of the ones that I'm going to talk about that we've done research on are activated carbon and membrane technology. So I'll talk about some research that we've got in those areas. If you haven't been to a water treatment plant, or you don't know how we treat most of our water, Long Island's a little bit of an exception because we have this huge source of high purity groundwater. But if we're looking at surface water sources where we're going to have these blooms, a lot more goes into the treatment of this water. So a typical conventional process for water treatment, where you have surface water that you might have a cyanobacterial bloom in, the water will come in. There'll be some screening to remove large branches and twigs and things like that. Tires, whatever gets thrown into the river or the lake. Then it goes into what's called coagulation and flocculation. And here we're trying to remove the solids, the suspended solid material. We add some chemicals, some coagulants. We mix them really quickly at first and then very gently to try to form big flocks. And those flocks then settle out. It then settles out in a big sedimentation tank. After that, we run it through some type of granular filter, usually a sand filter, or it might have some anthracite in it as well. And then we disinfect the water. Some locations put fluoride in for dental health. And then there's usually corrosion inhibitors. So this is in the news right now, right, with Flint. So they left this this step out, and very tragic consequences. But these are the basic processes. So coagulation, sedimentation, filtration. In the Midwest, where you've got a lot of limestone, you've got very high hardness in the water. So some treatment plants use what's called lime soda softening to remove calcium and magnesium. So not a lot of calcium and magnesium in our water here, so there's not any need for lime softening. This is really in areas with a lot of calcium carbonate in the soil. In terms of coagulation, there's been some previous work that shows that you can get very good removal of the cells, so the organisms. You can incorporate them into the flocks, and you can get removal of almost all the cells. But you don't get any removal of the toxins. And that's expected because this technology wasn't designed to remove trace compounds from water. There is a potential for the release of the toxins because you break up the cells. So there's these big mixing blades that move at up to 100 RPM very quickly that can break up these cells and release the toxins. So you want to really try to avoid mixing these in a way that might release the toxin. So that's sort of the main concern here. But try to optimize it to remove the cells and avoid releasing any of the toxin. You go into filtration. This is a picture of a typical sand filter. The water comes down here through gravity, flows through a sand layer typically, and then there's a manifold at the bottom that just collects the water. Hopefully most of the cells are gone by this point, and so this is more of a polishing step, but you will get removal of the cells. But again, sand doesn't absorb much, so you're not going to get removal of much of the toxin. And again, the cells can accumulate on this material, and so there's a potential for these cells to break down over time, and when they break down, potentially release the toxins. So there's some concern about the release of the toxins from these filters. Once it goes through filtration, we disinfect the water, and there's a lot of different disinfectants that we use. Chlorine is the most common disinfectant in the United States. I think over 80 or 90% of water supplies use chlorine as their primary disinfectant. But there's also there's other forms of chlorine. There's chloramines. There's chlorine dioxide. A lot of utilities will add potassium permanganate as an oxidant or ozone. And then there's also ultraviolet advanced oxidation technologies. So, questions? And then here are some of the toxins. And what I want to show here is that there's sort of no magic solution or magic oxidant to destroy these toxins. So if you look at chlorine, it's very effective at destroying microcystin and cylindrospermopsin, but it's not effective at destroying anatoxin or saxitoxin. Potassium permanganate is effective at anatoxin and microcystin, but not saxitoxin, or we don't know. So the challenge here is that to pick a particular oxidant is not going to be effective for every type of cyanotoxin that might be out there. Also, to use these to destroy these toxins, usually you have to use very, very high dosages, much higher than you'd use for the disinfection process. And if anyone has studied disinfection in drinking water, you might realize that this is a concern. The concern is that surface waters also have just background organic material like humic and fulvic acids. And when they react with these oxidants like chlorine, they form disinfection byproducts. Chloroform is the most typical example. And these are carcinogens. So if you add very high dosages of this, you may destroy some of these, but not all of them, and you have the potential to increase your disinfection byproducts. So jacking up the concentration of these is not really a viable option for dealing with these. Also, people, water treatment plants realize exactly how much chlorine they can add to their water until they're they start getting complaints. Where people turn on the tap and go, "This smells bad," and even though it's chlorine and it's not necessarily dangerous at the dosages, their phone starts ringing off the hook. So they know exactly where to kind of keep that till the complaints will stop. So disinfection can help, but it's not the solution. Okay, so a lot of treatment plants are moving to more advanced water treatment processes or different processes. And one of the major types of technologies that are being used are membranes. So about 20 years ago, we figured out ways to inexpensively produce membrane materials in a lot of different configurations. And this has opened up all kinds of applications in drinking water and wastewater. So there's different types of membranes. There's ultrafiltration, nanofiltration, reverse osmosis, basically based on the size of the pores. So ultrafiltration have very large pores, reverse osmosis very small pores. So the nice thing about these processes is they can really replace all of these. You can just get rid of all of these things. And you can just run the water through ultrafiltration, nanofiltration, reverse osmosis, and then disinfect it and put it in the distribution system. So it really removes a lot of these technologies, and a number of water treatment plants are moving to this new technology.
So how,
yes.
For a major city, urban center, with these tiny pores, how do you get enough water through there to satisfy the demand?
A lot of pores.
Yeah.
Yeah. So there's a couple of large desalination plants that have gone in. Tampa Bay was the first large desalination plant in the United States. There's one that just started up in Carlsbad, California, and so as the costs come down, these things become viable options. They're still more expensive than this, but if you're in somewhere like California, where there is no water, these things in that realm apparently seem to start to make sense. But even for lakes and non-saline water supplies, there's a lot of interest, especially just in the ultrafiltration piece. You don't necessarily need reverse osmosis in that case because you're not removing the salts. Okay, so we've been looking at ultrafiltration membranes and trying to understand how effective they are and how they work. So this is a schematic of sort of a porous membrane. So here's the membrane material. The water flows through these pores, and in a real system, these operate in a cross-flow mode. So what that means is that the feed water comes in, the water that you want to treat, say water from Lake Erie, if you're Toledo, it would come through here, and then there's a pressure forcing that water through the membrane to purify it, and then, but not all of it goes. Some of it is called retentate, and this is where sort of the concentrated contaminants would lie, and so there's essentially three different streams here. One feed coming in, the clean water coming out, hopefully, and then a retentate that would go to disposal. If we're talking about a cyanotoxin, let's see these little green circles, there's really two ways that this membrane might remove it. It can remove it by rejection. If the toxin is smaller than the size of the pores, just by size exclusion, it can't pass through the pores. Just like if you're straining something, the sieve, anything bigger than the size of the sieve is not going to go through. So you can get, that's one possibility. And that's a very good possibility. Let's say you have a cell. Let's say this bigger circle is a cell, a cyanobacteria. Those you have more likelihood of being rejected by size exclusion. And then the other possibility is that it can attach to the membrane material through absorption. Yes?
Could you tell me what is the typical pore size?
The typical pore size, well, these are called microfiltration membranes, so they're in the micron range. So it varies. It's a kind of a loose characterization. But you've got microfiltration, or I'm sorry, ultrafiltration is in the, let's see. Kilodaltons, yeah. Nanofiltration is about in the nanometer size. And reverse osmosis can really be in angstroms, very, very small. So you've got size exclusion and absorption is the two ways that you might see removal of both the cells and the toxins. The cells are generally much bigger than the pore size for ultrafiltration, so you'd expect them to be rejected by these. We've been looking at the toxins, and for the most part, these toxins are generally much smaller than the pores. So we looked at a variety of sizes here. Actually, I have some membrane materials here. This is our experimental setup. This is our cross-flow membrane unit. This is sort of our reservoir. And so we put microcystin in the reservoir. We pump it into the feed of the membrane. And then we have the water that goes through the membrane. This is the permeate. This is the treated water. This would be the drinkable water. And then we have the retentate, the water that gets rejected and that concentrates the contaminants. So what we did is we looked at a bunch of different membrane materials and sizes. So there's all kinds of different materials out there. And to get back to your point, your question, these are the sizes that we looked at. We looked at membranes anywhere from 1,000 Daltons to 30,000 Daltons. And that sort of spans the range of sizes that you would see for ultrafiltration membranes. And then we looked at a lot of different materials, cellulose acetate, polyether sulfone, polyamide, and a few others. So we looked at, they can be made out of all different kinds of synthetic materials. And one thing that we had to do that you typically wouldn't see was that we recycled the permeate and retentate back here into the tank. Microcystin is very hard to come by, so we were not able to produce it ourselves. We weren't in the production mode of making it. So there are some sources out there, but it's very expensive, and you get microgram quantities. So it's a very precious thing to work with. So we would recycle it. So our results are based on that. And I'll explain how that looks. So these membrane materials have all different types of properties in terms of their hydraulic properties, their charge on the surface, and their hydrophobicity. So we wanted to look at kind of a range of materials that are out there. These are the kind of results that we get. So this is the permeate concentration. So the water that goes through the membrane, so this is sort of the drinkable stuff that you would hope would be drinkable, as a function of time. And so the cellulose acetate membrane with a very large pores, what we saw is we started at about 50 micrograms per liter, and the permeate was 50 micrograms per liter. And so everything went through the membrane. Okay, so the pores are, it's like throwing a tennis ball through your garage, right? The garage is the pore, and the tennis ball is the toxin. Just shoots right through there. And so nothing's getting removed, and we just see basically nothing happening. The concentration just stays where it is. We recycle it back in here. It comes out. It's just we're circulating 50 micrograms per liter around and around. But interestingly, we saw, for example, on the other end of the spectrum, this is a polysulfone membrane. We saw nothing come out originally. And then it started to creep up a little bit, and then it reached a sort of a steady state and leveled off. So we were kind of wondering about this because this membrane was still, this one was $30,000. It was even bigger. So we wouldn't expect size exclusion. So what we determined was that it was absorption. It was absorbing to the membrane. And so as we start to run the water through here, initially it all absorbs. This is like an isotherm. If you've done absorption isotherms, all of the toxin absorbs, and then once the surface gets saturated, you start to get breakthrough. It's like a breakthrough curve. for if you've looked at contaminant transporting groundwater. So we saw that the polysulfone membrane really absorbed a lot of the membrane, and then because we're recycling it, it levels off, and then we ended up with 4 or 5 micrograms per liter that just then starts cycling through the system. No more can absorb. And then, then the behavior really varied depending on the particular membrane material. So we had, almost all of it absorbing here, and then increasing amounts or decreasing amounts of absorption until we got almost no absorption. So we're interested about sort of what the properties were that was resulting in this. And so if we go back here, we can see that really the contact angle correlated pretty well with the absorption. So we had the cellulose acetate membrane, we saw virtually no absorption. That one has a very low contact angle. Okay, so if you're not familiar with contact angle, what you do is you put a drop of water, usually on some kind of like a glass slide, and then you measure the angle at which the water bead gels on top of that glass slide. And so if the water bead likes the surface, it flattens out, okay, because the surface is hydrophilic. If it doesn't like it, then it beads up and you have a large contact angle. So the cellulose acetate had the lowest contact angle, meaning that it was the most hydrophilic membrane or the least hydrophobic. And the polysulfone membrane, where we saw the most absorption, the PS30, had the highest contact angle, meaning it was the most hydrophobic. And when we looked at all of these, we found that it roughly correlated with the hydrophobicity of the membrane. So using very hydrophobic membranes, you get a lot of absorption to the membrane surface. We did see some size exclusion. We looked at these thin film composite membranes, starting at 1,000 Daltons up to 4,000 Daltons. And 1,000 Daltons is roughly the size of microcystin. It's roughly about 1,000 Daltons in size. So we did see, we saw that the microcystin was rejected over time. So we did see some absorption because this keeps decreasing, but we saw that the 1,000 Dalton rejected more than the 4,000 Dalton pore size. So the difference between these 3 curves reflects the size exclusion. So we saw that if you have ultrafiltration membranes that have relatively large, small pore sizes, you can see some size exclusion in addition to absorption. One thing that we found that was very concerning was that these membranes can absorb the material. Periodically, a water treatment plant will backwash them. So they accumulate solids on the surface, and then you want to backwash it. And what we found was that if we absorb the toxin onto the membrane and then backwash it, we got a lot of the toxin back off. So it's very reversible. The absorption is very reversible, which creates an issue in terms of what do you do with that water, because now you've sort of got this concentrated brew of toxin in the water from the backwashing step, because you're running many hundreds, thousands of gallons through this, and then you're backwashing it with a very small volume, and so you're really concentrating that toxin. So this is a potential issue. We didn't get all of it off of the surface, but we got more than half of it back off the surface. We didn't feel that the absorption to the membrane was really a viable strategy because for removing the toxins, because you don't get much absorption really. Even in our small system, we saw it saturate the surface, and so it's not really a long-term treatment technology or approach. So what we looked at, we started to look at activated carbon. This is a common adsorbent used in water treatment for taste and odors, and so we wanted to look at how this activated carbon could be integrated into a membrane system. This is a picture of activated carbon. It's got different types of pores, very small pores. They're called micropores, mesopores, and macropores. And so there's different types of pore sizes and all kinds of different activated carbons. And a lot of work had been done on this. This is a previous study done by others that looked at 8 different types of carbon with different characteristics and correlated the absorption to the pore size. And what they found was that it was really the carbon that had a lot of mesopore volume was the best in terms of absorption. And that makes sense because the micropores are less than 2 nanometers. The toxins are pretty big. They can't access those pores. So that's a surface that's just not available for absorption. The mesopores are big enough for example, microcystin to get into, and it provides a lot of surface area. Macropores are big enough, but once the pores become very big, you start losing the specific surface area. So previous research has shown that these mesopores are the best type of porosity for removing these toxins. The challenge is that this is very different than other toxins a water treatment plant might want to use carbon for, like taste and odors. Geosmin, which is one of the odor compounds in surface water, is very small compared to these. So there you want really a lot of micropores to maximize the carbon use. So it's not one carbon fits all again, so it's a bit of a challenge. So what we did was we modified our system and we added carbon, PAC, that's powdered activated carbon, so it's a very fine carbon material. And we added this and then ran basically the same experiments where the carbon gets rejected from the membrane. There's bigger than the pore size of the membranes. So we're really trying to absorb the toxins onto the carbon, and then we use this to separate out the carbon. We use 2 types of carbon. We used one made from wood and one made from coconut. They had different porosities. I think I'm just going to show the ones with the better results here. And we use a few different types of membranes. These results are for cellulose acetate membranes. This is the amount of removal of microcystin. And for ultrafiltration alone, we saw no removal. Again, this made sense because they're hydrophilic. We're not getting any absorption to the membrane. When we looked at PAC absorption, we used one of the PAC, the wood-based activated carbon, which was the better one with more mesopores. We saw pretty good absorption here. And when we coupled them, we saw basically the same thing because we weren't really getting any additional removal from the membrane. When we looked at the polysulfone membrane, we saw roughly the same activated carbon absorption, but we also saw a lot of absorption to the membrane. So the combination of the two gave us, at least initially, even better removal when we combine the two. If you look at this, we're still at about 80%. So what we did was we wanted to try to get better removal of the toxin. So we looked at adding more carbon. So we looked at different dosages, 2 parts per million and 5 parts per million. And these are very typical numbers that you might see in a water treatment plant. So it's not like we're throwing a ton of carbon in here. Again, cellulose acetate with no carbon, we don't see any removal. And then as we add more carbon, we get more removal. And for the 5 parts per million, we could get almost complete removal of the toxins for microcystin at least. And then the same thing with the polysulfone. We see removal without any carbon because we get absorption on the membranes. But then when we add carbon on top of that, we get even better removal. Again, close to 100% removal. At the time, nanoparticles were sort of all the rage a few years ago, so we thought, okay, these iron nanoparticles might be a good substitute for carbon. So we looked at an iron nanoparticle called Maghemite as a potential substitute for carbon. And these are about 20 to 30 nanometers in size, very small. And we found that the absorption of microcystin on these was really dependent on pH. We saw at low pH, we got very good absorption at pH 4.4. But at higher pH, the absorption started to really trail off and not be very good. When we looked at sort of the maximum absorption at different pH levels, we found that the amount started off very high and then dropped. These are at 2 different concentrations, so we saw a drop in both. These actually collapse on the same curve if we look at the percent absorbed. So we saw almost everything absorbed at the low pH, but then it quickly dropped off. So what this meant was that this this particular material wouldn't be very good at absorbing the toxin if we're up at around pH 6 or 7, which you might see in a water treatment plant. We were interested to understand why, so we looked at the charge of microcystin. It's got different functional groups, so this is the protonation of different functional groups as a function of pH. The bottom line here is that once you get above about pH 3, it becomes negatively charged, the molecule. When you're down around pH 2 or 1, it becomes positively charged. So under most conditions that we're going to be working in, it's going to be a negatively charged molecule. The particles, we looked at the zeta potential. This is essentially related to the charge as a function of pH. We found that the point of zero charge, or isoelectric point, was about pH 8. And so below that, it's positively charged, and above that, it's negatively charged. So combining these together, it made sense that as the pH decreases, we get sort of more positive charge, and we still have negatively charged toxin, and so we get a lot of absorption. But once we get to very low pHs, they both become positively charged, and we start to see it decline. So we saw basically very consistent with this behavior here. Okay. So that's sort of I'll try to wrap up here. To kind of go back to my four main points, I'll say that the occurrence of these cyanohabs in drinking water is of increasing concern. Is it increasing the number? It's not clear. Possibly as we get more nutrients into our water and more eutrophication, but there's definitely more awareness of it, and so the concern for these in drinking water is increasing. The different types of cyanohabs make it difficult to control treatment because there's so many different physical chemical properties and sizes. For conventional water treatment, we want to effectively remove the cells, but they don't remove the toxins. So for things like coagulation, flocculation, we want to try to make sure that we do a good job removing the cells, but we don't want to break those cells apart to release the toxins. And then really the work that we've been doing has shown that membrane technologies and various adsorbents can be combined to get really high removal. We can get almost complete removal of these toxins under realistic conditions of using off-the-shelf membranes and activated carbon. I just want to thank Junju Lee and Yenling Liu were PhD students that worked on this. Yenling is finishing up her PhD right now. And then I have some other collaborators at Ohio State that helped with some of the membrane characterization. And then this has benefited a lot from Judy Westrick at Wayne State University. She's done a lot of work on the ecology and toxicology of these compounds. So again, I really appreciate the great audience here. I hopefully it's worth your time. And if you have any questions, I'll try to answer them. Yes. What's next? Well, there's a lot of places I'd like to go as department chair, and I need to find time. To answer your question, though, I mean, there's different toxins. All we've really been able to look at is microcystin, and just one type of microcystin. But there's a lot, as I mentioned, there's a lot of different toxins and a lot of different properties, and so I'd like to try to look at some of these other toxins and see if we can get similar results.
So I was wondering about the size or the scale of your experiments. Are these benchtop?
These are lab benchtop, yes.
So do you expect that what you are seeing there could be easily translated to like a metropolitan?
Metropolitan, yeah. There are full-scale pH activated carbon ultrafiltration membrane systems that are used. So in terms of the technology is there. Will we get 90%, 100% removal like we're seeing in the lab? That would need to be determined. I think the lab setup we use is Hydrodynamically, it's designed to be scalable, in terms of the properties of it. So there's a lot of thought that went into that cross-flow system to make sure that the hydrodynamic conditions roughly scaled to what you'd see in a full-scale system. But without doing it, I just speculate on it. But yes.
Is there any way? I mean, thinking of somebody who sometimes lives in a place where basically you're dependent on the homeowner to do the water quality. Could these things be manufactured into Brita cartridges or something, so that if there's a Brita, a microcystic bloom in Lake Erie, the homeowner could slap on a cartridge and at least protect themselves?
Yeah, well, Brita filters typically have activated carbon in them. So it's a mixture. It's really a mixture of ion exchange resin and activated carbon. So I haven't seen any data on a Brita filter in particular, but it certainly has the potential to remove these toxins. A lot more expensively, but
Yeah, well, that or not drinking water at all.
yeah.
This is going to totally show you my lack of knowledge of water treatment processes. But if you can put a charge on the molecule, can you use that for removal? Drop an anode into cathode into the solution and use that?
Yeah, you could do that from the water treatment perspective. The public demands a very low water bill. So generally, anything that involves electricity that becomes prohibitively expensive. An example for wastewater treatment, the biggest cost for wastewater treatment is typically the aeration. Just providing air bubbles makes it is the biggest cost that they incur. So to start charging electrodes and trying to move molecules by charge would become just very, very expensive. But it's doable. That's the thing about drinking water is we have the technology. I mean, we can turn anything into drinking water. From the water supply point of view, it's all about cost. You can give me the worst possible water, and I can I heat it on your stove and distill it, right? The technology exists to purify any water, but it's the cost that becomes the issue.
Regarding the absorption, it only happens on the surface of the membrane. I mean,
And the pores.
And the pores, right? So in that case, that is it possible that you can design the membrane which that with different configuration, therefore that the water going to passing through longer lenses through the membrane, therefore enhance of the contact area, enhance absorption.
You could. It's the challenge is that you want these membranes to be in operation for years and years and years. So I think it would be a challenge to have that much surface area for absorption. But you certainly could. You could have some improvement in it if you're able to increase the specific surface area of it.
So what about these desalination treatments? If you're using coastal waters, what are the implications for harmful algal bloom removal if you have?
Yeah, good question. That proposal wasn't funded, unfortunately. But yeah, about 15 years ago, they started proposing this reverse osmosis plant in Carlsbad, and I grew up like 10 miles from there, so I was like, oh, I know this. This is and they have these harmful algal blooms in the coastal areas of California. So I thought, okay, maybe this is something to look at. But I think that's a big issue where this is all fresh water.
Yes.
But for better or for worse, as we move towards using the ocean as a source of drinking water, which seems to be increasing really exponentially with time now, these harmful algal blooms in the ocean are going to be an issue. I mean, they use reverse osmosis, so they're going to be removed, but they're going to be concentrated. And so when you put the water back out into the ocean, you're going to sort of have a slug of these toxins.
I mean, the thing I was thinking about is microcystis clumps, and it's relatively large. If you have something like Alexandrium or something where the cells just lyse with,
waves crashing at the beach, you have a much more severe
Yeah.
problem.
Maybe you can give someone else a chance. Yeah.
So, related to what Mary asked, and the general use of water, why do you think we insist on using high purity water for all uses at the end? And rather than, I mean, many of us work on ships, for instance, so there's always a dual water use, one that you can drink and one that you can't, and that you don't care whether it has salt in it or other impurities. So one alternative here for the economics, at least on the water supply side, would be to split the kind of water you have at the user member and use potable water only in small amounts where you really need it. And all the other use, you can use gray water or whatever, and you don't care about these toxins unless they're volatile. So why aren't we, what I'm really getting to is why aren't we making our houses dual water supply systems where we have one that we drink and one that we flush our toilets with?
Well, that's a great question. When I teach water treatment, we design a water treatment plant in my class. We base it on the expected flow rate. And we assume that every person uses about 140 or 150 gallons per day. And that's based on national data. That's not based on estimates of a particular person. It's looking at all the water use in the United States divided by the number of people. It's 150 gallons per person per day. How much of that do you drink? That needs to be treated to these U.S. EPA standards. So very, very small, a gallon or two. There's certainly, if you're out washing your car, and your kids, when I was a kid, I took a drink right out of the hose the summer day. So there's those issues, but for the most part, there's no reason why the water we flush down the toilet needs to meet EPA drinking water standards. So it becomes an issue of the cost of the piping. But certainly, again, it's feasible to do it. It's not a technological challenge. It's simply what people are used to, the cost, and that kind of thing.
So on Long Island, I'm sorry, you ride around and you can see people just running this high purity groundwater down the street because they water their lawns with it with automatic sprinklers. I mean, most of it goes into waste.
When I
It's
moved,
an absolute crime, in my opinion.
When I moved here, 2012, everything is more expensive. My house is more expensive. My electric bill is more expensive. Food is more expensive. Taxes is more expensive. Water is cheaper.
So you just mentioned EPA regulations. In the beginning of your talk, you mentioned that there was a lack of regulation. I forget what level that was on. Can you remind me?
There's no regulations at the state or federal level now.
So I realized that, so at the state or federal level, I realized that these things may fluctuate regionally. What is preventing some kind of standardization of regulation? Do you have any thoughts on that?
Standard? What is, in terms of
just like a blanketed standardization
of what?
Regulations.
What? What's preventing that?
Yeah, what would you say would be preventing that?
I mean, at the federal level, I think the EPA is hesitant to ask until every I is dotted and T is crossed, and so there's still a lot of epidemiological. There's not a lot of data out there, in terms of the health effects compared to some other compounds. So I think that's probably the big issue at the federal level. The state level, some states don't even create their own regulations. So a lot of states, it's just not even an option. But then they need the resources to try to figure this out on their own, and that's a challenge. In the back?
Yeah, to address Bob's question, to start off, the best environmental book I've read, maybe in my life, is one that addresses the history and the future of water treatment and wastewater treatment and supply by David Sedlak. I recommend it to everybody, Water 4.0. But one of the issues that comes up with running 2 lines into the home, and there's other arguments, is unfortunately, he's a proponent of that, but is that every so often, rarely, people mix up the lines. And it's a real concern.
Yeah, I mean, I think from from a water supply point of view, I tell the students that we're treating the water so it's safe. Not most of the time, not usually, but we expect it's got to be safe all the time. I mean, that's the mindset that you've got to have. And so these things that might occur very infrequently are actually very, very, very big issues.
That's where Darwin comes in.
Okay, maybe let the gentleman in the back there.
Back on the politics of this, what are some examples of countries that do have a legal standard, and is there an overlying reason as to why they have it where the countries don't?
The question is, what are some examples of countries that have standards for this, and why do they have them, sort of on the policy side? I don't know. That's a good question. I can't. There's just a couple countries that have standards. I think I'm thinking Australia might have them, and I suspect that it's because they've got a critical issue here. They have a real challenges potentially bigger than ours. But on the policy side, that's a little bit outside my area. We do one more?
Mary, one more.
Yes, I just wanted to say, well, in the case where as these algal blooms become more common, or even other variable toxicity issues become more common, like in Flint, is there a way, or is it at all feasible to imagine having a sort of sideline where you normally don't run the water through a particular cleaning step, but when the microcystis bloom in Lake Erie happens, you would run it through this much more expensive section of the plant that might clean it up for the 2 weeks that the bloom lasts or whatever. And that would be a way of, sort of like the kitchen faucet Brita filter as opposed to the whole house water filter where you're only cleaning the water that you actually are using.
Yeah, that's what Toledo did actually. So the bloom in Lake Erie lasted most of the last half of the summer. So it wasn't just there for a day and then left. So what they do is they actually add this activated carbon, and then they remove it during that sedimentation step. They estimated that it cost them about at least an extra $1 million because they had to add a lot more carbon to their system, and by increasing the dosages, they estimated roughly about a little bit over $1 million extra that they had to pay to deal with this issue over that summer.
So probably cheaper than bringing the water in from somewhere else.
There's a lot of reasons why it's better than bringing water from somewhere else.
Well, thank you very much.
Thank you.